In the last video we analyzed the structure, emulated the first instructions with ESIL and discovered some components such as the interrupt function and reloading of the Active Directory Services module. A short addendum to the last video. The return value of load library XW, that is the handle for ntdsap.dll, is cached on the stack because we only simulated the function calls and do not know the start address of the DLL in memory. We just put the distinctive value hex .beef on the stack. We push hex 4037D1 on the stack, the value interpreted automatically as a string we see in the comment. Here we see the manual way. Furthermore, we push hex 4037C3 and hex 4023DO on the stack, pop the last value from the stack to EAX, and call the function whose starting address is in EAX. The Windows RP function lstrcat is called from kernel 32DLL. The second parameter is the address to our null terminated string kubruk. And the first one is an address to the empty null terminated string that should contain both strings after calling the function. Then we call getEnvironment variable a with the parameters lp_name, lp_buffer and nsize. We check whether we can read hex d byte from the environment variable vmq and so on, and jump in the positive case into the interrupt function hex 42237. The following code is identical to lines 6 through 17 and again checks for a file named klicksnick. The value at location hex 403714 is 0 and is increased by hex 2567A321. We cannot see any change because radare2 opens files without writing permissions. To open radare2 with write permissions, we can pass the -w option at program start, or we can use the command oo+ on the radare2 command line. In the last chapter, the handle of ntdsap.dll was written on the stack. Now we push exactly the starting address to EDX and increase the value by hex 3c. Does this value seem familiar to you? The metadata analysis in the first video showed that at the position hex 3c, the offset from the beginning of the file to the beginning of the PE header. Move EDX, dword EDX, moves the offset to EDX, and at dword ESP EDX changes our value on the stack from the ntdsap.dll starting address to the ntdsap.dll PE header address. And pop EDX pushes the offset itself on the stack as well. For the last instructions, pay attention to the difference between move EDX dword ESP and pop EDX. The first instruction does not change the stack pointer, the second however. Now we increase EDX by hex A4. At this address is the size of the base relocation table. We store it at the address hex 403772, save the value first in EAX, and then again at the address hex 403772 and in ECX. If the base relocation table is less or equal to hex 9f, we jump into the interrupt function hex 42237. If the table is greater or equal to hex A0, then we check whether it is greater than hex F70, smaller than hex F70, or equal. As a reminder, at the beginning of the last chapter we set hex 403714 to hex 2567A321. If the base relocation table is less than hex F70, hex 86 times 0 is added to the value and we continue executing the same instructions as if it were larger. If it is larger, hex 86 times 0 is added to the value in hex 3714 and jumped to the position hex 4022F9. We are also there if the size of base relocation table is exactly hex F70. All three paths led to the code block hex 4022F9. Here we'll fill EAX with hex CAD 8801E. Unfortunately, ESIL abandons us at this point and does not execute the command correctly, but pushes hex 35 to EAX, so we change EAX manually and put the value on the stack. Now we fill EAX with hex 3567A321 from hex 403714 and write the sum of hex CAD 8801E and hex 3567A321 on the stack, without increasing the stack point. We get the sum from the stack to hex 403714 through call dword hex 403714. In summary, this means that the function address depends on the size of the base relocation table, and we can guess without researching in the ntdsap.dll which address, in our case, is the right one. We have set ECX 1 less than hex F70 and go through the further instructions. We are in the middle of the code block hex 402328, writing hex 688 to EDX and pushing it on the stack, to then prepare the 3 parameters from the winrp heap create function by passing dw maximum size with hex 688, dw initial size also with hex 688, and FL options with hex 40000 to heap create in kernel 32 DLL. The option heap create enable execute gives him the right to execute code, so we create a heap with hex 688 bytes with a simulated starting address hex deadbeef. At the beginning of the chapter, the value hex 688 was written once too much on the stack. We pop this back to EDX now. We also check if heap create has returned a handle, which is the heap's starting address, by jumping into the interrupt function when EAX is 0. Now we are almost at the end of the source code, but it is surprising that we do not realize any damage to the system. Well, a lot can happen in a loop, so we should not throw in the towel too early. We set easy to hex 8D16F7D, copy the register EAX with the starting address of the heap to ECX, and write the value hex 40 to 8D0 into the register ED. As a last step in this code block, we push ECX on the stack. We write 4 bytes from address hex 40 to 8D0 to EAX, increase the value in AD by 4, and manipulate the 4 bytes in EAX. Firstly, we subtract to F. Secondly, we rotate a byte to the right. Thirdly, we subtract the value in register AZ and 1. Now we overwrite the value in AZ with the value in EAX and manipulate the 4 bytes in AZ by rotating 1 byte to the left. The manipulated first 4 bytes from address hex 40 to 8D4 we write in our heap and increase the starting address. Since we did not create a real heap, we skip these 2 commands. Finally, we reduce register EDX, which has the size of the heap, by 4 and jump to the beginning of the code block at address hex 402387, since EDX is hex 684 and not null. Today we got to know some new Windows RP functions, refreshed our knowledge about the header structure of portable executable files, and started to analyze the loop function. All this makes you suspect evil, but the real harmful effect has not yet been proven. In the next part we will reveal the secret of the looping function with the help of a faithful companion ESIL and a friendly snake. The last 5 lines of code will probably be analyzed quickly and go down to the deepest depth of the source code. Believe me, it will be scary.
See you later.